Hello students, welcome to standard 9 subject mathematics chapter 10 circles. This is lecture number 5. In last lecture we have seen theorem 10.5. Till that the theory we have seen, and exercise 10.3 was given in your homework. After that we have some more theorems, and they are related to equal chords and their distances from the center. About that we will discuss here. The equal chords we will see, and their distances from the center. What will be the relation between them, the distance and the chords, if they are equal chords, that we will see in the theorems. So theorem 10.6 is equal chords of a circle or of congruent circles. We have to take the equal chords, whether it is a circle means only one circle, in that the two chords are there, equal chords, or whether it is a two circles are there, congruent circles are there, in that also the equal chords you have to consider. So equal chords of a circle or of congruent circles are equidistant from the center or centers. That means if the chords are equal, they will be from equal distance from the center. So that is here, are equidistant from the center. If one circle will be there from the center, if congruent circles are there from their centers, they will be at the equal distances. This is the theorem. We will understand this theorem by drawing this figure. For example, we will take this circle is given with center O. In figure, if chords PQ and RS, two chords are there and they are equal, PQ equals RS, means equal chords are given, then the distances from the center, is O. So distance from the center to PQ is OL, perpendicular. To see the distance from any point to the chord or line, we have to draw the perpendicular. So OL is perpendicular on PQ, which is the distance from center to chord. And here also OM is perpendicular on RS, which is the distance from center to the chord RS. OL. So if PQ and RS equal chords, that is PQ equals to RS, then distance is OL equals to OL. In figure, if chords PQ equals RS, then the distances from the center to these chords are OL and OM, they will be equal. That is the theorem 10.6. Now theorem 10.7 is converse of the theorem 10.6. It is converse. In this theorem, what we have seen, the chords are equal, their distances from the center are equal. And in its converse, it will be reverse, you can understand. If the distances from the center to two chords are equal, if distances are equal, the chords will be equal. So how it is the statement? See, chords equidistant from the center, if the chords like PQ and RS are equidistant from the center, are equal in length, when the chords are equal in their length. In figure, in short, we explain this. Equidistant, this PQ and RS at equidistance from the center. So distance from the center is OL and OM. Equidistance means at equal distance, that is OL equals to OM is given. If this happens, that from the center two chords are at equal distance, then that two chords are equal. So that is then PQ equals to RS. So in short, what you understand from these two theorems, that if chords are equal, they will be at equidistance from the center. Next, if the two chords are at equal distance or equidistance from the center, they will be equal chords. Simple. This theorem we will use in the next coming example too. It is, if two intersecting chords, here we have to draw two chords which are intersecting each other of a circle, make equal angles with the diameter, and we will make the diameter in between them such a way that both the chords are making equal angles with the diameter passing through their point of intersection. Then prove that chords are equal. So this situation is shown here in a figure. This is the circle is given with the center O. In that two chords AB and CD intersecting each other at point E. So if two intersecting chords of circle that is we have shown here the intersecting chords of a circle AB and CD intersecting at the point E, and this PQ is passing through the point of intersection, that is A, diameter passing through the point of intersection that we have, point of intersection is E. So we have to draw the diameter passing through this E. So PQ is drawn in such a way that passing through E and it is a diameter also. And one more condition is here. With this diameter, this chord AB is making angle AEQ, this, and with this same diameter, this chord CD making angle DEQ. If both the angles are equal, if two intersecting chords of the circle make equal angles, these two angles are given equal. If these two angles are equal, we have to find AB equals to CD, means chords are equal. Let's prove this. So in solution, first we write the data. What is given here? So in the circle with the center O, it is given two chords AB and CD intersect at E, and PQ is a diameter through E, passing through E. PQ is a diameter, such that this is also given that this chord with the diameter making angle AEQ and the second chord CD making angle with the diameter as DEQ, both are equal angles given. So angle AEQ equals angle DEQ, it is given. To prove, we want to prove that the chords are equal. Chords are AB and CD, they are equal, that means AB equal to CD, we want to prove. So very simple proof we have here. To prove this, we will extra construct here something like construct OL is perpendicular on AB, we have constructed, and this side OM perpendicular on CD. On both the chords from the center, we have drawn perpendicular to show the distance. So OL is the distance from the center to this chord AB, and OM is the distance from the center to this chord CD by drawing perpendicular. Now in triangle LOE, this short, the smaller triangle you see, LOE, this small triangle you can see. In that, by angle sum property of a triangle, what is angle sum property of a triangle? You know, in a triangle, three angles are there, and sum of all three angles is 180. That property we have to use. So we are talking about angle LOE, this angle. If we want in this triangle, this angle, so we have to subtract from 180 the remaining two angles. So that we have done. So all total sum of 180 of three angles minus this angle L is subtracted. You can understand this is perpendicular drawn. So if perpendicular is drawn, this L angle will be of 90 degree, that is subtracted here, minus the next angle, remaining angle is LEO, that is subtracted. From 180, this angle 90 degree is subtracted and this angle is subtracted. So angle LOE we will get, that is here the expression you understand. In triangle LOE, this angle LOE equals to 180 minus remaining two angles, they are minus 90 and minus LEO. Now 180 minus 90 is 90, you know, minus LEO as it is. Then 90 minus LEO angle is actually this angle. LEO is this angle. Geometrically, this angle can also be said as angle AEQ, the same angle showing. So in place of angle LEO, we can write angle AEQ also. So that we have written 90 degree minus, in place of LEO, we have written angle AEQ because both are geometrically the same angle, only the name are different. Now that is equals to 90 degree minus, as it is, angle AEQ is equals to angle DEQ. So in place of angle AEQ, we can write angle DEQ because it is given. It is given in the question, equal angles AEQ equals to DEQ. Now again 90 degree minus this DEQ, you see the figure, angle DEQ means this angle. Geometrically this angle can also be written as angle MEO, that is we have written in place of DEQ, angle MEO. Now this angle MEO is subtracted from 90, 90 minus MEO. 90 minus MEO is actually in this triangle you see now triangle OEM. This is of 90 degree. So sum of the two remaining will be 90 degree. If I subtract from 90 any one of the angle, the other angle we will get. So this expression is 90 minus MEO. 90 minus MEO. That means it is showing this angle, and this angle name is angle MOE. That is angle MOE. So this as result 1. Now we take the two triangles here to compare. As you can see here, one triangle OLE and the other triangle is OME. This triangle and this triangle. We will make the list of equal things here. The first is angle LEO equals to angle MEO. Why? Because angle AEQ equals to DEQ is given. Angle AEQ equals to DEQ is given. And this angle AEQ can also be written as OEL or LEO, angle LEO. This angle AEQ is the same angle LEO, only the name is different. Equals angle DEQ can also be written as angle MEO, that is MEO. Because this is given, the same angles are represented by this different name. So these two angles are also equal. Next, in these two triangles, EO is common side or OE is common side. So OE equals to OE common side. And from the result 1, what we have proved, angle LOE, this at the center meeting angle, LOE equals to angle MOE. That is from the result 1 we have taken angle LOE equals angle MOE from result 1 we have taken. By showing this in these two triangles equal things, three equal things, what we have shown actually, angle LEO equals to angle MEO, that is these two angles we have shown equal. OE equals OE, that means this side we have shown equal, and LOE equals to MOE, means these two angles we have shown equal. So what they are representing actually in these two triangles, angle side angle on that triangle, and here also angle side angle on this triangle. So we have shown in given two triangles, the angle side angle, corresponding angles, sides and angles are equal. So by ASA, angle side angle, that is ASA, both the triangles will be congruent. This is the criteria for congruence of the triangle in chapter number 7, the triangle we have seen. So triangle OLE, congruent triangle OME, OLE, congruent triangle OME. We can write because of ASA. Now if two triangles are congruent, their corresponding parts are congruent. So by CPCD, we can say the first side OL equals to first side OL. What this represents? OL is the distance from the center to this chord, and OM is the distance from center to this chord, and the distances are at equal distances, the two chords. So by theorem 10.7, we know that chords at equidistance from the center. So these OL and OM equals, that means the AB and CD, two chords are at the equal distance from the center. So their chords will be equal. So the chords are AB and CD. So they will be equal by theorem 10.7, and that is only we wanted to prove that chords are equal. So we have shown that chords are equal. So this way we have seen the theorems here 10.6 and 10.7, and we have seen how to, using this theorems we can give the proof, or we can solve some examples and questions of the exercise. So this is the example 2 we have understand. Now the exercise 10.4 you have, that is your homework to do, exercise 10.4. So in homework you solve exercise 10.4, in which you will find that you have to use these theorems 10.6 and 10.7, and like this in example 2 we have used it, that way you have to solve.